Question number 4. 3 capacitors, 2 microfarad, 3 microfarad, 6 microfarad are joined in series with each other. The equivalent capacitance is option 1, 1 by 2 microfarad, option 2, 1 microfarad, option 3, 2 microfarad, option 4, 11 microfarad. Okay. Answer option 2. Answer 4, option 2. Answer 4 means answer for question number 4, option 2. This is the solution. This is effective capacitance formula when the capacitors are connected in series. 1 by C series is equal to 1 by C1 plus 1 by C2 plus 1 by C3. 1 by C series is equal to C1, C2, C3 are given 2, 3, 6. Okay. So you take LCM as 6. So 3 plus 2 plus 1, 6 by 6, which is 1, and reciprocal of 1 is also 1. So effective capacitance when the capacitors are connected in series is 1 microfarad, which is option 2. So it's a direct question. Simply apply the formula. Question number 5. 2 point charges placed in a medium of dielectric constant 5 or at a distance r between them experience an electrostatic force F. The electrostatic force between them in vacuum at the same distance r will be option 1 5F, option 2 F, option 3 F by 2, option 4 F by 5. The given answer. This is all official keys, okay? These are all taken from official key. So answer 5, that is answer for question number 5 is option 1, 5F. So this is the explanation. This is the two charges Q1 and Q2 in medium. K is 5. Formula F is 1 by 4 pi epsilon naught K. This K is dielectric constant Q1 Q2 by R squared. Then when they are in vacuum, F dash, the symbol which is used here is F dash 1 by 4 pi epsilon naught Q1 Q2 by R square. This is in free space or vacuum, this is in medium. And from this we get this is equal to K times F, but K is given as 5, so 5F. Okay, so this is also very clear. Maybe we can explain it this way. This is the medium value. Okay, what do? You multiply both LHS and RHS by K, right? So here also you will multiply by K. So this K and this K will cancel. So what remains is Q1 Q2 whole divided by 4 pi epsilon naught. Because this K has been cut, only R squared. But Q1 Q2 4 pi epsilon naught R square is nothing but F dash. So K times F is equal to F dash. This is the symbol used, okay, F dash. So F dash is force in vacuum, this is force in medium, but it is given K as 5. So 5F is equal to F dash. So force in vacuum is 5 times force in medium. So 5F is the answer. So it's given here as option 1. So this is the correct option. And one more thing, here it is given electrostatic force between them in vacuum in the question. But you see in the key, official key, force in the charges in the air. Force between the charges should come. So in the air, here vacuum, here air. Of course it's not a very big deal because for vacuum, the epsilon r value for vacuum, if you want, for vacuum you can write it as 1.0000000 for vacuum. Okay, for vacuum. For air, you know, the epsilon r value is say 1.00059 for air, 59. So almost equal. In the key it is air, it does not make any big difference, because for the epsilon r for air is only a little bit more, slightly greater, that's all. Otherwise it's fine. Okay, so the answer is this. We already have told this. One more thing, suppose if you forgot this formula, if you do not know this formula, still you can guess the correct answer, provided you know that force between two charges would be maximum only in vacuum. Other media it will be less. If you know this fact, without knowing all this formula, straight away you can hit upon this answer. See, it is given force in medium of dielectric constant 5 is F. Force in medium, it is given as F. So in vacuum it should be greater than F, provided you know that the force between two charges is maximum in vacuum. It is given here in medium it is F, so in vacuum it should be greater than F. Out of all these choices, only this is greater than F. Question number 6. Which statement is true for Gauss law? All the charges, whether inside or outside the Gaussian surface, contribute to the electric flux. That is option 1. Option 2, electric flux depends upon the geometry of the Gaussian surface. Option 3, Gauss theorem can be applied to non-uniform electric field. Option 4, the electric field over the Gaussian surface remains continuous and uniform at every point. This is the given answer. Answer 6. That is, answer for question number 6 is option 4. This one is given as the correct answer. This is the explanation given. All other statements except the option 4 are incorrect. It has to be one word. So are incorrect. The electric field over the Gaussian surface remains continuous and uniform at every point will be the correct option according to the key. Now we will analyze this. Which statement is true for Gauss law? All the charges, whether inside or outside the Gaussian surface, contribute to the electric flux. That we can check whether it is right or wrong. Consider this. This is the field lines due to a positive point charge. All arrows are pointing outward. Just for example, this case is considered. There is one Gaussian surface here, another Gaussian surface here. Even though they can be of any shape, I have just drawn circles indicating they are spherical, the three-dimensional counterpart. Now, whether this charge which is outside this Gaussian surface will contribute to the flux, that we have to check. Now, you take this field line. This field line enters the Gaussian surface and it leaves the Gaussian surface. So this field line enters and it leaves. So the field lines entering the Gaussian surface also leave the Gaussian surface when the charge is outside. Thereby, they do not contribute to the flux. They enter and leave, they enter and leave. Similarly here also, you see, this electric field line enters and leaves here. This electric field line enters and leaves here. This electric field line enters and leaves here. There is no effective contribution of these lines for the electric flux of the Gaussian surface. So when the charge is outside, they do not contribute to the electric flux. Is it clear? Therefore, we can say that this is not true. Not true. I'll simply write here for each statements or each options, then finally we decide. Then come to the option 2. Electric flux depends upon the geometry of the Gaussian surface. This we will check. Now consider the case which is shown here. See here, positive charge gives out electric field lines. This is the inner Gaussian surface, say spherical Gaussian surface. So see how many number of lines pass through it. Again you consider the cubical Gaussian surface enclosing the same point charge, same charge. Again the same field lines that are passing through the Gaussian surface which is spherical will also pass through the cubical Gaussian surface. The flux associated with the spherical Gaussian surface will be same as the flux associated with the cubical Gaussian surface. So it does not depend on the shape of the Gaussian surface, so long the charge enclosed is same for both Gaussian surfaces. Okay? Therefore, this is also not true, because it does not depend on the geometry or shape of the Gaussian surface, but here it says it depends. Therefore, this is not true. I said shape, but it is given geometry. That's fine. It means the same thing. Then Gauss theorem can be applied to non-uniform electric field. This is true. See, here he has given Gaussian surface. Here Gaussian surface. Even here Gaussian surface. But here Gauss theorem. So Gauss theorem can be applied to non-uniform electric field. True. Because we can find out the electric field due to sphere of charge, shell of charge, even due to point charge. So these electric fields are non-uniform, but still we use Gauss theorem to find the value of the electric field. Right? So Gauss theorem can be applied to non-uniform electric field is true. Fine. Then the electric field over the Gaussian surface remains continuous and uniform at every point. Here the wordings are not all that proper, so somehow we will have to bear with the wordings. See here, this is Gauss theorem. Integral E dot ds or dA, anything, so long it represents area vector. We know that this is Q enclosed by epsilon naught. See, in the Gauss law or Gauss theorem itself, here Q enclosed. Therefore, this can also be the reason for this. All charges, whether inside or outside, but here charge inside only is given in the law itself. So this way also you can address this. Yeah. Now coming to this fourth option. Electric field over the Gaussian surface remains continuous and uniform at every point. I said already the wordings, you will have to bear with the wordings. So here you can see, if the electric field is along the area vector, the electric field vector, area vector are in the same direction, we can write this as EDS. Of course, Q enclosed by epsilon naught. Modulus of A dot B is modulus of A, modulus of B, cos theta. Theta is the angle between A vector and B vector. Similarly, E dot ds can be written as modulus of E, modulus of ds. Angle between them, if theta is 0, cos 0 is 1, so it will vanish, provided vector E, vector ds are in the same direction. Then when this is uniform, in the sense that if it is constant, it can be taken outside during the integration operation. If you want to integrate, no, so E can be brought out, which enormously simplifies the integration process. So for that, E should be constant. Constants can be taken out, and it has to be continuous. So here, uniform instead of uniform, or even if it is given as uniform, you take it as constant. So this is true, so that the evaluation is easier. It facilitates the evaluation of the integration process. So this is true. Wordings only little bit this way and that way. So two options are true, option 3, option 4. But given answer says only option 4 is correct. According to key, option 4 is correct.